Hello students, welcome back. In the previous video, we stated and proved this theorem. In a system of m homogeneous linear equations, I forgot the term homogeneous, m homogeneous linear equations with n unknowns, that is either this way or equivalently in matrix expression like that. If n is greater than m, which means if there are more unknowns than number of equations, then the system has a non-trivial solution. We already know the trivial solution exists. Plug in all zeros and something times 0 is 0. Yeah, that's true. We already know one solution. Are there any more? Well, if there are more than one, if there are more unknowns than number of equations, then the answer is yes. There are more solutions. Non-trivial solutions. If there is one, then there are infinitely many more, as a matter of fact. It was difficult to prove. We used mathematical induction, and also we combined it with proof by logical implications, but we went through it. If you weren't able to follow everything there, that doesn't mean you cannot utilize this one. So let's use it from this point on. Now let's go over to the next section and let's talk about how to solve a system of linear equations, not using human brain, but in completely algorithmic fashion, as if you're designing a computer. And that kind of thing is called Gaussian elimination. And the theoretical background beneath this Gaussian elimination can get a little bit deep, as a matter of fact. It establishes the existence of, or the possibility of, triangular matrices, triangulation, and so on. I'll try not to go that deep, but we still have to talk about the elementary operation, and here we go. Let's begin. Let's suppose we have a matrix expression of a system of linear equations like this. It's a non-homogeneous system. And then one way to express the same thing is to use something called augmented matrix. Just assume this whole thing, which I'm running my mouse around, is the same as that matrix. And then if you use just one color, then that can be a little bit tricky. And the last column represent the right-hand side of the equation. Now I'm using multiple colors, so I'll do my best to separate this last column using different colors. But even if you see some black and white textbook, well, our own textbook is like that, by the way, and without any separator, you'll have to assume the last column is the right-hand side. So augmented matrix simply means a system of linear equations. In general, if you have this kind of system, and let's just put the last column over here, and this expression and this single matrix are equivalent. And then you can design or prove with the algorithm to solve the system of linear equation, and that is called elementary row operations. What do you mean by elementary row operation? We do a repetition of these three. Multiply a non-zero number to its entire row. So for example, here in this row, multiply each by, say, 7. That's equivalent to multiply 7 to left-hand side and right-hand side of the equation, so no change. Multiplying by -1, again, no change there. So this elementary row operation does not change the outcome of the system of the linear equation. Make sense? So applying that to augmented matrix, we're going to keep the same solution. Next, add one row to the other. Add equation. And that's something we have been doing for elimination method, right? Just multiply something to a certain row and then add it or subtract it to another row. And that's basically it. Add one row to the other. And then interchange two rows. So first row became third row becomes first. And that is nothing more than just changing the order of equations. So that's really duh. So all those do not affect the outcome of this system of linear equations. And then if you apply those repeatedly to the augmented matrix, basically you're doing the solution using the elimination method. Do we have an example? Okay, let's have this an example here. Okay, let's solve the system of linear equation using this Gaussian elimination on augmented matrix. Okay, let's begin with augmented matrix. So this matrix and then put this one as a last column and this one. Do you see? This equation, this form and that are equivalent. Do you see that? Okay, all right. Our purpose is to triangulate it. So though anything below, down here, we want all zeros. That's basically what we want. Okay, let's begin. Let's switch the order, row 1 and row 2. Let's switch those because I want 1. I want something that begins with 1. That's simpler. Okay, all right. So first row, second row. Okay, did everybody follow? All right. This is where we are right now. And now R2 minus 3 times R1 and then put it into R2. So multiply 3 to this entire row, first row, and then subtract it from R2. Okay, that's an element, that's actually a combination of several elementary row operations. But here we go. So multiply 3 to this and subtract from that, and that'll kill off that 3. That's the purpose. So we want it completely algorithmic, basically making these zeros and next zeros as if computer is doing the computation, at least to a certain degree. So if you do all the computation, you're going to get that. Oh, it's really tedious computation. It's really pain in the rear end. Anyway, another computation, row 3 minus twice of R1 and then put it into, oh, a typo. It should go to R3. I'm doing a computation through row 3, so okay, it should go to R3. So let's see. Multiply 2 to this one so that if we get 2 and subtract, that'll kill off this 2. And if you do it right, you're going to get this. Multiply 2 and subtract, 2 minus 2 is 0. Multiply 2 and subtract, negative 1 minus 2, so this is negative 3. Multiply 2 and subtract, 3 minus of negative 2, so we have positive 5. And then 0 minus twice of this, so 2. 4 minus twice of negative 2, so it's basically 4 plus 4, so we have 8. Kind of like that. So we are done with these. So first equation just gives me x1, and the others do not have any x1 anymore. As a matter of fact, this form here is equivalent to this expression. Come on. Oh, never mind. Let's try anyway. Okay, I don't need this part anymore. And then, okay, this, okay, all right. So augmented matrix means this. This thing, the last column is the right-hand side. And then after some elimination, what did you get? X appears only in the first row, and then the other do not have any X in there. You see? One by one, we are removing characters. That's the way we do Gaussian elimination, isn't it? And we are doing it in a little bit simpler form, using only the coefficient without all the X's and Y's and things like those. And that technique is using augmented matrix and elementary row operations. Okay, this is where we are so far. And then what's next? R2 minus twice of R3. R2 minus twice of R3. If I do that, -5 and then minus double of this, so -5 plus 6, that'll make this one into 1. Yeah, I want to get 1. And then, indeed, that's what I got. And then you have to follow the same thing to all the other numbers. Good luck. This is what you got. Okay, next, let us eliminate the others. So, R3 plus 3R2. So multiply by 3 and then add them up. So I can eliminate this one and make it into 0. And then the others are affected through the same operation. And this is what we get. And what is this? That last expression is equivalent to this. This is always the right-hand side. So we got up to here. X appears only in the first row, and Y appears second row and first row, and here, neither X nor Y appears in the third row. So we got simpler expression. And then, of course, we can eliminate this 1 as well, as a matter of fact. Subtract R2 from R1, and then remove this one as well. So Y appears only in the second row. We can do that. It's not completely algorithmic that way, but I prefer to do it that way, to tell the truth. But our textbook's method is to leave everything up here and then just remove all these zeros and then diagonalize into 1. So let's do this. Divide everything by -13. Not everything, excuse me, row 3. And this is what we get so far. So, what's the interpretation of this augmented matrix? Before doing that, excuse me, I thought I already had it in my clipboard, but don't. So, okay, let's go back here. Okay, I don't need this part. And then we got up to here, all these numbers. And then the right-hand side is the last column of this augmented matrix. So this augmented matrix is the same as this equation, matrix equation. And then if we rewrite it in terms of traditional form, we have this system of linear equations. That's the interpretation of all these. Okay, is this better? Yes, indeed. We can start from down below. You can solve z from w and then plug those into the next. And z is expressed in terms of w, so y can be expressed in terms of w. And plug into the first. W is there, z is something w already done. Y is expressed in terms of w, so you can solve x with respect to w. You see, you can do all those. Indeed, this is a solution. Start from down below, and then the next. So for y, and then the first, and so for x. So everything is solved with respect to w, and this is what we get. X is 1 over 13 w minus 4/13, and so on and so forth. This is perfect answer, but those who are interested in vector geometry may want to do this. Separate w times this vector plus the vector, and then w times that is actually a scalar multiplication of certain vector in direction. So write it as w over 13 and then 117,513. So this is a direction and starting from a certain point. So what is this? This is a point, and then this is a direction. You're looking at a line starting at this point at the direction of this 117,513 vector. It's a 4D space, so I cannot even begin to draw this, but it's a line anyway. Well, if you're not really into vector geometry, never mind. That kind of deep vector geometry is not supposed to be covered in linear algebra anyway. Of the 3D we used to cover, but we move it over to calculus 3. Anyway, verification. If you run Mathematica, you're going to get a solution. Oh, never mind. Okay. Did I erase everything here? Okay, and we have a little bit of time left, so let's go with the second solution. Let's do the same thing. Let's do it a little bit more quickly this time. Let's see. Matrix we obtained at the end of 6. What is this? This augmented matrix over here? Okay. That can be simplified a little bit further. Basically what we want is, I want more zeros. So subtract R2 from R1 and then replace, then I'm going to kill this one. So subtract, and then this one becomes 0. You get that? So we have 1, 0, 0, 0, 1, 0. Okay. And then I can kill off these two as well. 5 and negative 6. Basically, I can multiply 5 to the third row and subtract from first, and 6 times the third row and then add to the second. That way I can kill these two as well. And that's what we did. And is it simpler than before? Well, let's see. What is the interpretation of that? I don't need this part. And this means that is equal to this. Okay? That's what the augmented matrix means. The last column is the right-hand side. And then if I rewrite it in terms of, let's see. Okay, if I rewrite it in terms of system of linear equation, oh yeah, it's here. X, no y, no z, and then w. So x minus 1/13 w is negative 4/13. So this is the first row. And then the second row, no x, no z. So y minus 17/13 is the right-hand side, this one. And same goes here. No x, no y, just z. Z minus 5/13 w is that. So we can solve x, y, and z using w directly with these. And of course we get the same solution as before. Assume all this computation is done algorithmically by a computer, not by a human, then this kind of computation makes a lot of sense because this is completely algorithmic. And that's what this thing is developed for, as a matter of fact. Not for students' paper and pencil computation. It's going to be impossible, as a matter of fact.